Good morning, everyone. So let's start our second day of our workshop. And it's a pleasure to introduce for this plenary talk, Professor Krzysztof Eiral from Institute of Mathematics, Polish Academy of Science, Poland. He's professor at the Institute of Mathematics of the Polish Academy of Science in Warsaw, IMPAN. His areas of interest are singularity theory, algebraic geometry, and topology, with main focus on the geometry and topology of complex singularities. And he will talk about zeta functions and mu-star Zareski pairs of surfaces. Thank you very much, Krzysztof.
Thank you very much for this introduction. It's a great honor for me to give a talk in this wonderful workshop, and I really would like to thank the organizer for giving me such an opportunity. I'm particularly happy to participate in the celebration of Professor Saiki's work and 60th birthday, so happy birthday, Professor Saiki. Unfortunately, I was not able to come in person in San Carlos this time, but I hope I can see you all very soon. So today it will be an online talk. Let me put my screen like this. And in this talk, I will present a joint work with Mitsuoka about mu-star Zareski pairs of surfaces. So before giving a precise definition, let me explain the problem we are interested in. So for that, I consider two polynomial functions, G0 and G1, both of them from C30 to C0. So as usual, this notation means that the origin of C3 is sent to the origin of C. And I will assume that the corresponding surfaces in C3, defined by the zero set of G0 and G1 respectively, have an isolated singularity at the origin. Then all of you know this very well-known theorem by Lee and Tessier. Suppose that these two surfaces have the same embedded topology, which means that the pairs C3Bg0 and C3Bg1 are homeomorphic in a small neighborhood of the origin. Or if you prefer, this is the same as saying that the corresponding pairs of embedded link are diffeomorphic. So here S5 epsilon is the sphere in C3 with the origin as center and epsilon as radius, and Kg0 is the link associated with G0, which is simply the intersection of this sphere and the surface. So saying that these two surfaces have the same embedded topology is equivalent of saying that the corresponding pairs of embedded links are diffeomorphic, of course, if epsilon is chosen sufficiently small. Then under this assumption, you know that G0 and G1 have the same Miller number. It is also perfectly known that the converse is not true. It is quite possible for G0 and G1 to have the same Miller number, but different embedded topology. However, in practice, if I give you G0 and G1 with the same Miller number, or even with the same Tessier mu-star sequence, here the Tessier mu-star sequence of G0, for example, is denoted by this symbol. It's a triple, which consists of the Miller number of G0 at origin, the Miller number of its generic plan section, and its multiplicity, precisely multiplicity minus 1. So if I give you G0 and G1 with the same Tessier mu-star sequence, so in particular with the same Miller number, then in general it is quite difficult, very difficult to determine whether or not the corresponding pairs of embedded link are diffeomorphic or not diffeomorphic. So the goal of this talk today is to present a class of pairs of polynomial functions G0 and G1 that have the same Tessier mu-star sequence, but which are likely to produce non-diffeomorphic pairs of embedded links. I simply say here which are likely to produce because, of course, our final dream is to show that any pair in this class will produce non-diffeomorphic pairs of embedded links. But this is quite a difficult problem, and we don't have a full answer to it at this moment. So today I will simply give a first step to this problem. That's why I simply say here which are likely to produce. So the pairs of polynomial function or the pair of surfaces in this class are precisely the mu star Zareski pair of surfaces that I'm going to define precisely now. So to define mu star Zareski pair of surfaces, the first thing I have to do is to define what is a simple Zareski pair of surfaces. This notion was introduced last year by Mitsuoka, and the definition relies on the well-known notion, which is the notion of Zareski pair of projective curves. So a pair of projective curves, C0, C1, in the complex projective plane P2, is called a Zareski pair if there exists regular neighborhood, tubular neighborhood, N0 and N1 of C0 and C1, respectively, such that the pairs N0, C0 and N1, C1 are homeomorphic, while the pairs P2, C0 and P2, C1 are not homeomorphic. This condition here on the regular neighborhood is equivalent of saying that the curve C0 and C1 have the same combinatorics. I recall you that the combinatorics of a curve is a set of data associated with the curve, which consists of the set of its irreducible component, the set of the degrees of this irreducible component, the set of the singular point of the curve, the set of the topological types of this singular point, and at each singular point, the set of local branches of the curve, together with a map that assigns to a local branch the global irreducible component that contains this branch. So all this set of data is called the combinatorics or the combinatorial data of the curve. And we say that two curves have the same combinatorics if there is a bijection between these two sets of data for the curve C0 and C1. So this homeomorphism here is equivalent of saying that C0 and C1 have the same combinatorics. This is not obvious at all. So we can rephrase the definition by saying that a Zareski pair of curve is a pair of curves C0 and C1 that have the same combinatorics, so in particular the same degree, the same singularity, and so on, but different embedded topology. The very first example of such a pair was given by Zareski himself in 1930. In this example, the two curves are sextic curves, so curves of degree 6. They are irreducible, and they have both 6 cusp singularities. So in particular, they have the same combinatorics, and we have such homeomorphism. But in the first case, the 6 cusps are all located on the conic, while in the second case, they are not. There is no conic passing through the 6 cusps. And this difference between the position of the singularity, the location of the singularities, affect a lot the embedded topology of the curve. It turns out that these two curves have different embedded topology. So to show it, Zareski simply compute the fundamental group of the complement of the curve, and in the first case, he finds the non-abelian group, and in the second case, he finds an abelian group. So anyway, now we know what is a Zareski pair of projective curves. We can define the main notion that we are interested in, which is the notion of Zareski pair of surfaces. So we start with the Zareski pair of projective curves, C0 and C1. I assume that they are defined by reduced homogeneous polynomial F0 for C0 and F1 for C1, and I will denote by D the common degree of F0 and F1. And now I look at the affine surfaces in C3, which are defined by the polynomial G0 and G1, which are simply obtained from F0 and F1 simply by adding the same term of this form, Z1 in a power D plus N. So D is the common degree of F0 and F1, and N is simply an integer greater or equal to 1. If you want, you can add Z2 or Z3. It's the same. So we say that the pair of surfaces Vg0, Vg1, or simply the pair of polynomial G0, G1, is a Zareski pair of surfaces if G0 and G1 have an isolated singularity at the origin and the same zeta function. So in particular, the same lunar number. In this talk by zeta function, I always mean the zeta function of the monodromy associated with the mean of vibration of G0 and G1 respectively. So for example, if you start with the Zareski pair of projective curve given by Zareski, so 2 sextic curve with 6 cusp singularities, and if you add, for example, here the term Z1 in a power 7, then G0, G1 is a Zareski pair of surfaces. This is not obvious at all. This is a very special case of the main theorem that I'm going to give now. So to fix well the notation and to state the theorem, let me consider again a Zareski pair of projective curves, C0 and C1. I still denote by D, their common degree, and I assume that C0 is defined by this reduced homogeneous polynomial F0, and C1 is defined by this homogeneous polynomial F1. Now, it is not difficult to see that by a linear change of coordinate, we may always assume that these two polynomials are convenient. Convenient means that the Newton diagram of F0 and F1 intersect each coordinate axis. It is not difficult to see also that these two polynomials are Newton non-degenerate on any phase delta of their common Newton diagram if this phase has dimension less than or equal to 1. Of course, F0 and F1 can be degenerate on the maximal dimensional phase, which is of dimension 2. But by a linear change of coordinate, it's not difficult to see that on lower dimensional phase, they are Newton non-degenerate. And also, we can always assume that the singularities of the curve C0 and C1 are not located on the coordinate line. So to produce such a system of coordinate, you just start with a 3 line, L1, L2, L3, that does not contain the singularity of the curve. And by a linear change of coordinate, you can move a little bit the line so that they intersect transversally the curve C0 and the curve C1 at exactly D point. And then you define the coordinate Z1, Z2, Z3 simply by Z1 equals 0 is the first line, Z2 equals 0 is the second line, Z3 equals 0 is the third line, and you get your system of coordinate which satisfies these three conditions. So that is done. Now we consider as before the polynomial G0 and G1 obtained from F0 and F1 by adding the same term like that, Z1 in the power D plus N. So the theorem says that in this framework, if in addition the singularities of C0 and C1 are Newton non-degenerate in some suitable local coordinate, so this means that at each singular point of the curve, there is a local system of coordinate, so that the defining polynomial in this coordinate near the singular point is Newton non-degenerate. So under this condition, we can show that G0, G1 is a Zareski pair of surfaces in the sense that I have defined 3 minutes ago. But that's not all. We can also show that G0 and G1 have the same Tessier mu star sequence, while they are lying in different path-connected components of the mu star constant stratum. A Zareski pair of surfaces that satisfy this second condition here, so G0, G1, same Tessier mu star sequence, but they are in different path-connected components of the mu star constant stratum. So such a pair is called the mu star Zareski pair of surfaces. And this pair of surfaces are precisely the pairs I was talking about in my introduction at the very beginning of the talk. So still referring to this introduction, I want to make the following observation. Of course, being a mu star Zareski pair of surfaces does not imply that the corresponding pairs of embedded link are not diffeomorphic. But at least it is a necessary condition for that. Why? We argue by contradiction, and we use two theorems. One that I will mention in a few minutes, and another one which is due to Tessier. Suppose that G0 and G1 are in the same path-connected component of the mu star constant stratum. So this means that you can find a path, continuous path, connecting G0 in G1 in this stratum. We have proved that in such a situation, we can also always find a piecewise complex analytic path connecting G0 and G1. But in this situation, Tessier proved that for each member on the path of the family, which is one parameter family, the diffeomorphism type of the embedded link is independent of the parameter. So if we have such a path, necessarily the embedded link for G0 must be diffeomorphic to the embedded link of G1. So if your goal is to construct a pair of functions G0 and G1 so that the corresponding pairs of embedded link are not diffeomorphic, then it is a necessary condition that the function G0 and G1 lie in different path-connected components of the Mustard constant stratum. So this theorem is not an answer to the problem I mentioned in the beginning of the talk, but at least is the first step to it. So now, in the remaining time, I will try to explain how we prove this theorem. So the first things we have to show is that G0, G1 is a Zareski pair of surfaces. So to simplify, I will simply denote G0 and G1 by the same letter G. And similarly, F would be either F0 or F1, and C either C0 or C1. So to show that G0, G1 is a Zareski pair of surfaces, we proceed as follows. First, let me make an observation. If G0 and G1 were Newton non-degenerate, then we could have simply used a theorem by Varchenko, which asserts that in this special case, the zeta function of G0 and G1 depend only on their Newton diagram. And since, of course, G0 and G1 have the same Newton diagram, they will have the same zeta function, and we are done. But of course, G0 and G1 are not Newton non-degenerate. They can be degenerate on the maximal dimensional phase, so we cannot apply Varchenko theorem. However, last year, Oka generalized, extended Varchenko theorem to a larger class of functions, which include Newton non-degenerate function. And he called the function in this larger class almost Newton non-degenerate function. So basically, an almost Newton non-degenerate function is a convenient function which can be degenerate on the maximal dimensional faces of the Newton diagram, but which are Newton non-degenerate on lower dimensional faces. And so what you recognize is that these two conditions that I put here, convenient function, which are Newton non-degenerate on faces of lower dimension. Of course, here the condition is on F0 and F1, but you have exactly the same condition on G0 and G1, because G0 and G1 is just F0 and F1 with this term, which is above the Newton diagram. But that's not all. To be an almost Newton non-degenerate function, the function should also satisfy two other conditions. The first one is that they can be degenerate on the maximal dimensional phase, but not in any way. They should have a finite number of one-dimensional critical loci. That is the definition in general in Cn. But in C3, with three variables, this condition is automatically satisfied. And the second additional condition is that after an appropriate toric modification, in our case, the blowing up will be enough, the singularities of the strict transform of G0 and G1 must be Newton non-degenerate in some appropriate local coordinate. And here you can almost recognize the condition that I put in the theorem here, except that this condition says that the singularity of the curve are Newton non-degenerate, while in the definition for an almost Newton non-degenerate function, it is the singularity of the strict transform that must be non-degenerate. But we will see in a few minutes that they are exactly the same. So to summarize, in our situation, under our assumption, the function g, which can be G0 and G1, satisfy Oka's almost Newton non-degeneracy condition. And then we can apply the formula by Oka, which gives the zeta function. And this zeta function, which is represented by this symbol here, zeta function of G, is given by this expression. So this expression has three terms, one here, one in the middle, and one on the right. And I'm going to explain now what they mean. So to do that, let me consider the blowing up at the origin, which I denote by this symbol. Then, clearly, outside the surface dg, the blowing up morphism is a bioromorphism. So this means that you can lift the mean of vibration of G at the origin to X. So that if you look now at the pullback of G on the inverse image of this space, you can recognize that the space between the bracket here is just the total space of the mean of vibration of G. You have a ball center at the origin with radius epsilon, and you take the intersection with the inverse image like G of a small punctured disk with radius delta, small compared to epsilon. So the space inside the bracket here is just the total space of the mean of vibration of G. You take the inverse image of that and you look at the pullback on it. And of course, this is a locally trivial vibration. And because outside the surface pi is a biolomorphism, this locally trivial vibration is isomorphic to the original mean of vibration of G at the origin. So that is the first observation. Second observation. Let's consider the standard affine chart, U1 of P2, with the standard coordinate, Z2 over Z1, Z3 over Z1. Capital Z1, Z2, Z3 are the homogeneous coordinate on P2. And then, in the corresponding chart of X, which is simply given by C3 times U1 intersected with X, I consider this coordinate. So the first one is small z1. So small z1, z2, z3 are coordinate in z3, and capital z1, z2, z3 are homogeneous coordinate on P2. So the first coordinate here is small z1. And the second and third coordinate are just this coordinate that come from the chart U1. So I will denote, to simplify, this coordinate simply by y1, y2, y3. It's not difficult to see that in this coordinate, the pullback of G has this expression. So he has two factors, one factor here, y1 in power d, which correspond to the exceptional divisor, and a factor here, which correspond to the strict transform. Clearly, outside the exceptional divisor, the strict transform has no singularity. Now, on the exceptional divisor, y1 equals 0, you can see that the strict transform is defined by this polynomial. But this polynomial, you recognize that this is just the defining polynomial of the curve C. So that the singularity of the strict transform on the exceptional divisor are just given by the singularity of the curve. And now we understand better the assumption that I made in the theorem, saying that the singularity of the curve are Newton non-degenerate is the same as saying that the singularity of the strict transform are Newton non-degenerate. Okay, so now what we do is as follows. For each singular point P of the curve, or if you prefer, for each singular point P of the strict transform, we consider the local mean of vibration of the pullback of G at this point. And we decompose the lifted mean of vibration, this one, as the union of the local mean of vibration at the singular point of C and the vibration over their complement. So what Oka proved is as follows. The zeta function of the function G, which is the same as the zeta function of the pullback of G, because these two vibrations are isomorphic, is given by the product of the zeta function associated with the local mean of vibration at the singular point of C, and this corresponds to the third term in the formula. You recognize here the zeta function of the pullback of G at a point P, where P is a singular point of C. Sigma C is the set of singular point of C. So you take this product and you multiply by the zeta function associated with the fibration over the complement. And this zeta function over complement corresponds to the product of the two first terms in this formula. So now the formula is almost clear. This term is perfectly clear. The term in the middle, there is nothing to do. I just have to tell you what is mu tot C. This is the total minor number of C, which is the sum of the local minor number at the singular point of the curve. And it just remains to explain this term. So this term is a zeta function of a certain function Hs. What is Hs? Hs is a one parameter deformation family, which is a deformation of G, which is obtained simply by taking a small perturbation of the coefficient of G in such a way that for S not equal to 0, Hs become Newton non-degenerate. Since we make a small perturbation only of the coefficient, we don't change the Newton diagram. So that will be for after. So this term is just the zeta function of such a function. Of course, I should take it for S not equal to 0, because for S equals 0, I just find the function G. So now these three terms in this formula are clear, and we are ready to apply it to our situation. So let me erase that. So I will use this formula and to show that the zeta function of G is the same when G is equal G0 or G1. And for that, we have to remember the main assumption of the theorem. So let me come back for a while. This assumption says that the singularities of C0 and C1 are Newton non-degenerate in some appropriate coordinate. So I'm just writing that. There exists a local coordinate x near a singular point P0 of C0, and local coordinate u near a singular point P1 of the curve C1, such that in this coordinate, the pullback of G0 and the pullback of G1 are given by this expression and this expression respectively. So they are of the same type, and you can recognize that this is exactly the same expression that I gave here. Simply now, I change the coordinate here to make this polynomial Newton non-degenerate. And I can do that thanks to the main assumption of the theorem. So this polynomial now is Newton non-degenerate, and this polynomial is Newton non-degenerate. So now, if the singularity P0 of the curve C0 is topologically equivalent to the singularity P1 of the curve C1, then we can also assume, this is famous theorem in the literature, that the Newton diagram of these two Newton non-degenerate polynomials are the same. So altogether, what we have that the pullback of G0 and G1 are Newton non-degenerate, and they have the same Newton diagram. So we can apply now the Varchenko theorem, which says that the zeta function, the corresponding zeta function, depend only on this Newton diagram. And since the Newton diagram is the same, they have the same zeta function. So the zeta function of the pullback of G0 at the point P0 is the same as the zeta function of the pullback of G1 at the point P1. Of course, provided that P1 and P0 are topologically equivalent. But this is the case. We have a Zareski pair of curves. So the singularity of C0 are the same as the singularity of C1. Anytime you take the singular point P0 on C0, you have the corresponding one on the curve C1. So what we have proved that in this formula, the third term here is exactly the same for G equal G0 or G1. So the second step is to show that the term in the middle is also the same. But this is obvious because the total minor number of C0 is exactly the same as the total minor number of C1. Again, because C1, C0 is a Zareski pair of projective curves, and then they have the same singularities. So this term is the same, this term also. Now we have to look at this term. So I recall you HS is the deformation of G, which is obtained simply by a small perturbation of the coefficient of G in such a way that HS is Newton non-degenerate. Since we move only the coefficient, the Newton diagram for the deformation for G0 and the deformation for G1 are the same. So this function is also the same by Valesteros theorem. The zeta function depends only on the Newton diagram. So this function is also the same for G equals G0 and G equals G1. So altogether, each term here will be the same when G equals G0 or G equals G1. So altogether, the zeta function of G0 and G1 are the same, and G0, G1 is the Zareski pair of surfaces. So that one thing, now we have to prove that this pair is mu star. So to prove that the pair is mu star, the first things we have to show is that G0 and G1 have the same Tessier mu star sequence. In fact, we can give an explicit formulation of what is this mu star sequence. It's given by this triple. So you have here the Miller number, here the Miller number of a generic plane section, and here the multiplicity -1. So to compute the Miller number is not difficult. We just use a standard formula. The Miller number is always given by -1 minus the degree of the zeta function. But the zeta function, we know it. We just use the Oka formula. So we have to compute separately these three terms. This term here, we have the zeta function of a Newton non-degenerate function. So we can apply, for example, Valesteros formula to compute this term. The term in the middle, there is nothing to do. And here we have also the zeta function of a Newton non-degenerate function. So again, we can apply Valesteros formula to compute this term. Then we take the product, the degree, and you will find immediately that the Miller number is equal to that using this formula. To show that the Miller number of a generic plane section is given by d-1 square is not difficult, because if you take a generic plane, the restriction of F to this plane is Newton non-degenerate. So the restriction of G to this plane is also Newton non-degenerate. And because they have the same Newton diagram, they have the same Miller number. But now the Miller number of a generic plane section of F is just the Miller number of a homogeneous polynomial of degree d. And that you know that it is d-1 square. And for the multiplicity, there is nothing to do. So the mu star sequence is given by this triple. And of course, because the total Miller number of C0 and C1 are the same, because C0 and C1 is the Zareski pair, then G0 and G1 have the same Tessier mu star sequence. So now comes the difficult part of the proof. We have to show that G0 and G1 lie in different path-connected components of the mu star constant stratum. So to do that, we argue by contradiction. Assume that they are in the same path-connected component. Then we have proved the theorem that I already mentioned a bit before. So by assumption, there is a continuous path in the mu star constant stratum that can connect G0 and G1. In this situation, you can show that there also always exists a piecewise complex analytic path, or if you prefer a piecewise complex analytic family, GS, for S a real number between 0 and 1, connecting G0 and G1 in the mu star constant stratum. Here, by a piecewise complex analytic family, we mean the following. We mean a continuous path, gamma, from 0, 1 in the mu star constant stratum, which assign to S the function GS that appear in this family here, together with a subdivision of the interval 0, 1 by some subinterval SQ plus 1, such that each of these subintervals is contained in some open set of C. And on this open set UQ, there exists a complex analytic map, gamma q tilde, which coincide with gamma when they are restricted to the subinterval. So that's exactly what we call here a piecewise complex analytic family for S between 0 and 1. So I'm not going to prove this result. The proof is given in the paper because it is a bit technical, but basically the idea is to interpret the mu star constant stratum as a semi-algebraic set. And then you use the Noether normalization theorem. And you get this theorem after several pages of computation. So, to summarize, now we have a piecewise complex analytic family GS such that the mu star sequence of GS is independent of this. So, in particular, this implies that the multiplicity of GS is constant because the multiplicity is just a part of the mu star constancy. This, in turn, implies that the initial polynomial of GS, denoted by this symbol here, has degree D. This is clear. But we can also show, and this will be an important property for what follows, that this initial polynomial is reduced. And that is not obvious. So to show that, again, we argue by a contradiction. Suppose that the initial polynomial of GS is not reduced. And then we will get a contradiction with the fact that the Milnor number of a generic plane section of GS is constant. So take a generic plane H with coordinate X and Y, and you write the generic plane section of your polynomial as the product of a linear form L1, LQ with some power here P1, PQ. By a linear change of coordinate, we can obviously assume that the first linear form is just given by X. So you have here a term X in power P1. And all the other form, I just write it simply by H. Because the polynomial is not reduced, we can assume that the exponent P1, that appear here, is greater than or equal to 2. And that will play a fundamental role. To visualize a little bit all that, let me give you some picture. Here on this part here, I draw the Newton polyhedron of the generic plane section of my initial polynomial. So what is important to observe is that on this boundary here, when you get this point here, the coordinate of this point here is P, which must be greater than or equal to P1. So in particular, this point P here is greater than 2 or equal to. That will be very important. In the picture, I also draw the Newton diagram of the generic plane section of G0, which is exactly the same as the Newton diagram of the generic plane section of F0. So you have one segment like that with coordinate D here and D here. And I also draw the Newton diagram of the generic plane section of GS. So in this picture, he has 3 segments, this one, and this one. And because this initial polynomial has degree D, you get a point here which is D plus some non-negative number E, and similarly here, D plus some non-negative number C. If the polynomial is not convenient, you can add I power of X and Y to make it convenient, so that we intersect each coordinate axis. That's nothing. So now let me consider 2 Newton numbers. I denote by nu, the letter for the Newton number. So the Newton number of the generic plane section of GS and the Newton number of the generic plane section of G0. We can compute this Newton number by classical theorem of Kushner-Renko, and I write the formula just below. So to compute this Newton number, what you do, you take the area of this triangle plus the area of this triangle and plus the area of this triangle, and you multiply by 2. Then you subtract this point and this point, so minus D plus C minus D plus E, and you add 1. That's just the formula of Kushner-Renko. And you do the same to compute this Newton number. You take the area of this triangle, you subtract this point and this point, so minus 2D, plus 1. And now the essential observation is that the area of this triangle depends on P. And P is greater than or equal to 2. So if you compare the two values that you obtain here and here, you will get that because P is greater than or equal to 2, the Newton number here on the left is strictly greater than the Newton number here on the right. So altogether, what do we have? We have that the Miller number of the generic plane section of GS, which usually we denote by this symbol in the Tessier star sequence, is greater than or equal to the Newton number of the generic plane section of GS. This is a famous theorem by Kushnirenko. The strict inequality in the middle here between these two Newton numbers is just what we have proved here. And this Newton number, if you compute with this formula, you find exactly that it is d minus 1 squared. But d minus 1 squared reminds you something. If I come back a little bit earlier, it reminds you that this is the Miller number of the generic plane section of G0. So I just write it. D minus 1 squared is the Miller number of the generic plane section of G0. So altogether, we have that the Miller number of the generic plane section of GS is strictly greater than the Miller number of a generic plane section of G0. And this is a contradiction because the family GS is mu star constant. So necessarily, the polynomial, the initial polynomial here is reduced. Then the third ingredient of the proof is a formula by Acampo that give you some expression for the zeta function. This formula says that the zeta function of GS can be uniquely written under this form. So we have a product of term of this form, 1 minus d di in exponent ui. So the di here are all mutually disjoint. Of course, the formula of Acampo is much more precise. If you want to have the precise formula, you have to take a good resolution of the function GS, then you decompose the total transform as the union of the strict transform and the irreducible component of exceptional divisor. And the integer here is just the multiplicity of the pullback of GS by the good resolution along each irreducible component of the exceptional divisor. And the integer nu here is just minus the Euler characteristic of the irreducible component of exceptional divisor minus all the other irreducible component and minus the strict transform. But we don't need to be so precise. We just have to know that by the Acampo formula, the zeta function is written uniquely as a product like that with the di mutually disjoint. Then I can define two things. We can define the zeta multiplicity of GS, that will be the minimum of this integer di that appear in this product. I will denote this multiplicity by m zeta GS. And we can also define the zeta multiplicity factor of the zeta multiplicity of the zeta function, which is that the factor 1 minus tdi nu I that appear in this product when di is exactly the zeta multiplicity. And then we have the following lemma. I recall you that the family GS is a mu star constant family. So by the theorem of Tessier that I already mentioned, this means that the diffeomorphism type of the corresponding embedded link for each member of the family is independent of the parameter, is independent of S. And this, of course, implies that the corresponding zeta function of GS is also independent of S. So that is just the result by Tessier. So in particular, what we have that the zeta multiplicity and the zeta multiplicity factor are also independent of S. And in fact, we can compute explicitly what is the zeta multiplicity and what is the zeta multiplicity factor. They are given like that. The zeta multiplicity is simply equal to the standard multiplicity of GS, which is D. And the zeta multiplicity factor is given by this expression. So you can see that it depends only on the degree D of F0 and F1, and the total minor number of some curve CS. What is CS? CS is the curve defined by the initial polynomial of GS. And now you understand that it was important that this initial polynomial is reduced, because if the initial polynomial is not reduced, all the points on the curve are singular. If you have a reduced polynomial, you have only a finite number of isolated singularities, and the total minor number is the finite sum of the minor number at each singular point of the curve. So it was very important to observe before that the initial polynomial of GS, which is the defining polynomial of this curve, is reduced. So to obtain this formula, I'm not going to show it, but you just apply the Acampo formula and it's not difficult to get it. So what do we have? This is the zeta multiplicity factor, and we know that the zeta multiplicity factor is independent of S. So this immediately implies that the total minor number of CS that appear here is also independent of S. And now we are almost done. We can conclude our theorem thanks to two other theorems by Ley. So the first theorem says the following. Assume that there is a bifurcation of singularities in the family GS, say at some point S equal S0. And assume that this bifurcation is contained in a small ball B, which is centered as a singular point, P0 of the curve C S0. What does this mean? This means that P0 is the only singular point of the curve CS0 in the ball, and it is either a newly born singularity or a singularity which is obtained as a merging of several singularities of the curve CS for S close to but not equal to S0. If you prefer, we can explain that in some other way. Consider this space here, the space of the pair PS in P2 times 0,1, where P is a singular point of the curve. And look at the projection of the first factor. Saying that there is a bifurcation of singularity in your family for S equal S0 exactly means that S0 is a point where this projection fails to be a covering map. For example, you can visualize in these two pictures. So this space here is here and here. Here I have the projection on 0,1 and this is 0,1. So you can see that for a generic S, if you take the inverse image here, you have 1, 2, 3, 4, 5 singular points. But when S approaches S0, these 2 points merge into 1. In the picture on the right, on the generic fiber S here, you have 1, 2, 3 singular points. And when S approaches S0, you have a newly born singularity that appears here. So that's what we mean by bifurcation of singularity. So now I will erase that. So the theorem says that if there is such a bifurcation of singularity at S equal S0, then for S close to S0, but different from S0, the sum of the minor number of the curve CS at a singular point P, which is contained in the ball, is strictly less than the minor number of the curve CS0 at the singular point P0. But what this implies? This implies that if there exists such an S0, so if there exists a bifurcation of singularity, then the total minor number of the curve CS is strictly less than the total minor number of the curve CS0. But this is a contradiction. We have just observed that the total minor number of CS is independent of S. So this is a contradiction. So what this means? This means that in our family, there is no bifurcation of singularities. But then we can conclude with the second theorem of Ley, which says that if there is no bifurcation of singularities, then necessarily the topological type of the pair P2S must be independent of S. But this is in contradiction with the fact that C0, C1 is a Zareski pair. If the topological type of this pair is independent of S, this means that P2, C0 is homeomorphic to P2, C1. And this contradicts the fact that C0, C1 is a Zareski pair. So we get a new contradiction, and we have proved our theorem. So thank you very much for your attention. And again, happy birthday, Saiki Sensei.
Thank you very much, Christophe. So first, I'd like to know if there are some questions from the YouTube channel. No? There are some questions from the audience here.
Good morning. I would like to know what happened if you change in the definition of G0 and G1. This term that appear above of the Newton diagram change for G0 and G1 because you have something like Z1 M plus D.
Yes. You want to know if we add the term which is not above the Newton diagram, then everything is destroyed.
Now, if the two monomials are different, what happens if you consider two?
If the two monomials are different. I didn't look at this case. No, I don't know what's happened. This is a different situation, yeah? I had exactly the same monomial. If the monomial are different, then I don't know what's happened. So something different may happen.
Okay, thank you.
It's not clear. It's not clear.
Okay.
More questions or comments here?
This is awesome. Thank you very much for your very nice talk. In some explicit examples, did you already try to show that the link 3 manifolds, they are not diffeomorphic to each other?
What is not diffeomorphic?
Sorry?
Can you repeat?
So you can try to find some examples such that they are not diffeomorphic to each other. For that, maybe you can try to show that the link 3 manifolds, not embedded one, just the 3 manifolds are not diffeomorphic to each other. For example, if you can compute the resolution diagrams, and if they have different resolution diagrams, then maybe they are not diffeomorphic. Just
yes.
as 3 manifolds.
Okay, find an example when it starts not with a Zareski pair of projective curve, but a weak Zareski pair, which means that there is no homeomorphism between the neighborhood. Yes? If you start with that, he constructed one example in which the link are not diffeomorphic. So in this case, in this special case, we answer completely the problem.
So you mean that you can construct
we have only one example with specific equation.
Yes. So you mean that you have some explicit examples?
Yes.
Such that
Oka published a paper with that, with an explicit example. He starts with a weak Zareski pair with explicit equation, and he showed that the corresponding link are not diffeomorphic.
Okay. Okay.
And in particular, the embedded link are not diffeomorphic either, of course.
Okay. Thank you very much.
Only one example with explicit equation.
Okay. Thank you.
More questions or comments? So thank you very much, Christophe. Merci beaucoup.
Thank you.
Let's thank the speaker again.
Good morning. It's my pleasure to introduce Professor João Carlos Quejer Acosta. He is a lecturer at IBUSE, Unesp of São José do Rio Preto. And he is a very long data, my friend, and a very good football player also. Not better than mathematics, but okay. And he's going to talk in a joint work with Erika Batista and Ingrid Sarmiento. And his talk is on the topological classification of circle-valued simple Morse-bot functions. Thank you, João.
Thank you, Marcelo, by the introduction. I would like to thank the organizers for this opportunity. For me, it's a pleasure to be here in São Carlos, where I have many friends and collaborators. And it's a pleasure to celebrate the birthday of Professor Zareski. The title of my talk is on the topological classification of circle-valued simple Morse-bot function. This is a joint work with Erika Batista from Universidade Federal do Cariri, Brazil, and Ingrid Sarmiento from Universidade Federal de Itajubá, Brazil. I would like to thank the FAPESP and CAPES by the financial support. What is the main goal of this talk? The main goal of this talk is to investigate the topological classification of circle-valued Morse-bot function from M2 to S1 up to topological conjugacy, where M2 is a closed, connected, orientable surface. We present here a complete topological invariant, which is a graph, so-called here Mbhb graph. This is our main result. And in the last part of the talk here, we indicate some open questions and work in progress. This talk is based in 2 papers. The first one is dedicated to M is equal to standard sphere. And the second one is a generalization of the first one. To understand this main goal, is necessary to understand some ingredients of appear here. What are Morse-bot function? Why do we study circle-valued function? What does topological conjugacy mean? And how can we define Mbhb graph? Okay? Let's start introducing these ingredients. Morse-bot function. Morse-bot function are a generalization of classical Morse functions. But what's the difference? The difference is that the singular set consists of isolated points and of submanifolds of bigger dimension. In fact, we need to define a non-degenerated singular submanifold to define Morse-bot function. Let F be a smooth function on a manifold M. A smooth submanifold S in the singular set of F is a non-degenerate singular submanifold of F if the boundary of F S is empty, S is compact and connecting, and for all P, the Hessian of F restricted to the normal space to S is non-degenerate. This third condition means that F restricted to the normal direction is a Morse function. And a function F is Morse-bot function or just MB function if the singular set of F consists of isolated points and also non-degenerate singular submanifolds. For Morse functions, we have the classical Morse lemma, which describes the local structure of F near a non-degenerate critical point. The local structure of F is a quadratic form. For Morse-bot function, we have a similar lemma. This is a Morse-bot lemma. The Morse-bot lemma gives also a description of F after a change of coordinates in a neighborhood of a point P, where P is in S, where S is a connected component of the singular set of dimension K. Then we can express F in this form, a sum of squares. Observe that if K is equal to 0, where K is the dimension of S, we have the classical Morse lemma, okay? Because if K is equal to 0, we have the classical Morse lemma. Some example of Morse-Bot function. The first is a trivial example. Morse functions are trivial Mbhb Morse-Bot functions with Morse functions are Morse-Bot functions with isolated singular points. We don't have submanifolds of bigger dimension, just dimension 0. From Morse-Bot lemma, we take that this example F is a Morse-Bot function, but is not Morse. And another example is the Wigner functions. The Wigner functions has many applications, for instance, in nuclear physics. More details about this kind of functions can be found in our 2 papers. Here is a picture associated to Wigner functions, where here we can see that 0 is a non-degenerate singularities. Here we have a submanifold of dimension 1, here also. How can we characterize the non-degenerate singular submanifolds in our case? Because in our case, we are working with a 2-dimensional closed orientable surface manifold. Then the non-degenerate singular submanifolds can be of 2 types, dimension 0 or dimension 1. Then the non-degenerate singular non-degenerate singular submanifold, which appear in the singular set of F, are subdivided in 3 types. Isolated points, like in Morse case, maximum, minimum, or saddle points. But also we can have a singular submanifold homeomorphic to S1. We observed that in our definition, the submanifold, the singular submanifold, non-degenerated, is a connected. Then the only possibility is S1 in this case. The second ingredient. Why consider this kind of function? Why consider circle-valued Morse-Bot function? Because circle-valued Morse-Bot function is different. The study of this kind of function is different of classical Morse-Bot function taking values in the line. For instance, the global properties are quite different from the classical Morse-Bot function defined in the line. For instance, there is an example of circle-valued Morse-Bot function from torus to S1 with no critical points, while classical Morse-Bot function taking values in R has at least 2 critical points. Okay. The first proposition says that if M is a simple Morse-Bot function and the Euler characteristic of M is non-zero, then F is always singular. Simple here means that F has only one non-degenerate singular submanifold for each level curve. Another motivation for me to study the circle-valued functions comes from the topological classification of finitely determinate map germs. For instance, when we are interested to study the topological classification of map germs from R3 to R2, finitely determinate, the topological type of this kind of function is determined by the link of F. And the link of F is a map from S2 to S1 if F has isolated 0. Then I started this study of circle-valued function because this fact, okay? In this case, the link is a Morse function and simple also. This is a stable map. This is another motivation to study this kind of function. But the definition, the formal definition of circle valued Morse-Bot function are just locally Morse-Bot function. Then, if you have M and F taking values in S1, for each X in M, you take a neighborhood V of Fx and a diffeomorphism phi in the line. We look F minus 1 of V, and we define this composition. If this composition, the F is a Morse-Bot function, if this composition is a real-valued Morse-Bot function, okay? An example, in this example, we have the sphere, and S1, and F given by the radial projection. In this case, the critical points are the saddle point, minimal point, or maximal point, like this. In this case, we have an example of Morse-Bot function from S2 to S1. In fact, here is a Morse function because the critical set are isolated points. One more example, here we have the B-torus, and we also consider the projection, the radial projection, as in the picture. In this case, we have two saddle points here, and also we have submanifolds, non-degenerate submanifolds, S1 circles, okay? What kind of topological classification are we interested in? When we study the classification, the classical classification of maps or map germs in singularity theory, it's natural to look at C0A equivalence. C0A equivalence is the equivalence given by change of coordinates in the source in the target of the map of the germ. But here, our definition, the change of coordinates in the source, we require that send singular fibers into singular fibers, because if H is just a homeomorphism, then could send singular fibers into regular fibers, for instance. To avoid this situation, we require that H sends singular fibers in singular fibers. This is natural condition. And K, the change of coordinates in the target, we require that preserves orientation. It's a natural because we want to give an order in the critical values. Finally, we define Mbhb graphs. First, we start reminding of the classical Hib graph. Classical Hib graph were introduced by Hib in 1946 to study Morse functional closed manifolds. Hib graphs are defined for continuous functions, defined on topological space. The Hib graph is a space obtained by the contracting the connected component of the level sets of function to points. When you contract the level set, the singular level set, we have vertices, and we contract like this regular level set, we have a point of the edge here, okay? Then this saddle is this, and this is this, contracting the level curves, okay? One more example from classical Hib graph. Hib graph is not always a finite graph. This is an important observation. But for a smooth function defined in a closed manifold with a finite number of critical values, Professor Saek showed that this quotient space is homeomorphic to a finite graph. And also in our case, when we are considering Morse-Bot functions from M2 to S1, in our case, also we have a finite graph, okay? And our graph has more additional extra information than the classical Hib graph. And why to consider a graph as an invariant? Because graph is a simple object. Then, for instance, to study graphs are as an invariant is simpler than, for instance, algebraic invariant. Then this is a motivation also. Then let's start the graph structure of Mbhb graph. Consider the following equivalence relation on M2. 2 points are related if only if they have the same image, where x and y are in the same connected component of the preimage of fx. And when you take the quotient space, this quotient space has a graph structure, called here a f, where the vertices are the connected component of the critical level curves, because V here is a critical value, and the edges is formed by points correspond to the connected components of the regular curves, regular level sets. Okay. Here we have a difference with the usual case in the definition of Mbhb graph, because in general, when we define Mbhb graph, the classical Mbhb graph, is required that the critical level contain the critical point. Here, no. Then, for us, appear more kind of vertices. We call these vertices regular vertices, different from classical case. Here we have the possible incidence rules of edges and vertices in our graph. A point of saddle, a maximum minimum. Here is a regular vertex. And here is a vertex given by the S1, the critical S1, submanifold non-degenerate of dimension 1. And this kind of vertex we call a white vertex. Okay? But we need to consider one more information in our graph related to the topological classification of eights on closed-oriented surface. And this classification was done by Ingrid Sarmiento, Reginelene Oliveira, and José Martínez Alfaro. This analysis play a key role to define the Mbhb graphs. Since we are interested to obtain a global invariant, we need to know how the saddle points appears immersed in M2. An H can be looked as an immersion of S1 in M2. It's important to investigate the different types of the H's. It's not sufficient to distinguish the topological type of the circles. A H is formed by two circles, but this does not distinguish the different types of H. It's necessary classification of eights, okay? And how can we do it? To classify the eights, we consider B, a singular fiber containing the saddle point. Okay, B is this curve. We call this curve the saddle curve, which is homeomorphic to an H. And consider VB, this region, the regular closed neighborhood of B. VB is homeomorphic to a sphere minus 3 disks. Then it has 3 boundary curves. This boundary in red and these 2 boundary in blue. The special curve when JB is the curve that is contractible to B. This curve, which is contractile to B, we call JB, okay? And let C be the function which associates each saddle vertex of the graph structure to the edge that contains the JB curve. Then in this case, the JB curve is here, then C is indicate the effect of we indicate the effect of C in the graph by the symbol star. Then we put a star here to identify that in this side is JB curve in this case. Okay. Let's finally to define our graph. Let V1 VR in S1 critical values of F. We choose a base point, V0, and an orientation of S1. He can reorder the critical values, and we label each vertex with the index I, if they correspond to critical value Vi. Then now it's possible to define Mbhb graph. The graph given by the structure graph RF, together with the labels like this, colors of the vertex, black and white, and with the function key, which assign the star in the graph, as previously defined, is called Mbhb graph associated to a simple circle valued f from M2 to S1, and it's denoted by gamma f. If M2 is equal S2, the standard sphere, there is only one topological type of saddle curve. Then, in this case, it's not necessary to label the edges that contain points associated to Mbhb curves. It's not necessary. But when M2 is not equal S2, is necessary. Moreover, when M2 is equal S2, the structure of the Mbhb graph is simple. It's a tree. Here we have one example. F and G are given from sphere to S1 to simple Morse-Bot function given by radial projection. This radial projection, then this F is not surjective. This G is surjective map. Here we have the Mbhb graphs associated to F and to G. Note that in this case, F and G are not conjugated and are not topologically conjugated because they are not topologically equivalent in this sense here. And if we consider classical Hib graph, the classical Hib graph is the same in this case, but the Mbhb graph is totally different. Then classical Hib graph is not sufficient to distinguish these two maps, okay? Another example, here we have this F and this G. Note that in this case, if that without the symbol star, without the symbol star here and here, the graphs are the same. But their Mbhb graphs are different in this case because the topological type of the saddle curves are not the same. This is the importance to put the star here, okay? Is the difference of the topological type of the saddle curve. Some remarks. The Mbhb graph was inspired on the invariants introduced in two PhD theses, a thesis of Érica Batista and a thesis of Ingrid Sarmiento. However, this graph, the Mbhb graph, contains some extra information, okay? The graphs of Érica and Ingrid is not sufficient to distinguish this kind of things. Another observation, if F is not surjective, then F may be regarded as simple from M2 to R via stereographic projection, and we can, in this case, apply just the result of Ingrid Sarmiento, okay? Then our case here is important when F is surjective. This is different from the Ingrid case. It is obvious that the labeling of the vertices in the Mbhb graph is not uniquely determined, since it depends on the chosen orientation in the base points on each S1. Different choices will produce either a cyclic permutation or an inversion of the labeling in the Morse-Bot or in the Mbhb graph. This allows us to introduce the following notion of equivalence between Mbhb graphs. We say that two Mbhb graphs are equivalent, and we denote by this, if there exists graph isomorphism J, preserving the assignment of the function key, and L, defined in S1 with a graph structure whose vertices are the critical values of F, such that the following diagram is commutative. Here VF is the vertices of the gamma F. Delta is the discriminant set, okay? Then we have our main results. First, we prove that the Mbhb graph is an invariant. If F and G are topologically conjugated, then their respective Mbhb graphs are equivalent. This is easy to prove. But the converse is more difficult. The converse proves that the invariant is complete. If the graphs are equivalent, then F and G are topologically conjugated. What's the main strategy of the proof? The main strategy of the proof is the following. From equivalence of the graphs, we have graph isomorphism J and L as in the previous definition. From this graph isomorphism, we construct appropriate local homeomorphism in certain regions of M2. And after this, we glue these regions to extend of a convenient way the homeomorphism for all M2 to realize the topological conjugacy. These are the steps to prove this theorem. Example, the two simple Morse-Bot functions considered in the first example are not topologically conjugated because their respective Mbhb graphs are not equivalent. The graphs have the different number of vertices, for instance. These maps are not topologically equivalent, conjugated. Note that if we do not consider the regular vertices in the Mbhb graph associated to F and G, then this graph would become indistinguishable and hence equivalent. Then this shows the importance that consider regular vertices, because this function in this example are clear not topologically conjugated. One is surjective and another is not surjective. Some open question and work in progress. A natural question is about the realization problem of graphs. When a finite graph is the Mbhb graph of a circle-valued Morse-Bot function? This is an interesting question. We answer this question when M2 is the standard sphere. We have a theorem, a big theorem. It's technical theorem. We give him many conditions to guarantee that a graph can be realized as a Mbhb graph associated to a simple Morse-Bot function from S2 to S1. But when we consider just the realization problem associated to classical Hib graph, we have many authors interested. For example, Charco, Matsumoto, Professor Saeki, Michalak, Gelbuck, Mesa Sarmiento, among others. But in our case, we are interested in realization with Morse-Bot or with circle-valued Morse-Bot function. And we have a work in progress investigating the realization problem of Morse-Bot of Mbhb graphs for other class of manifolds, but it's not trivial problem. We start studying the torus, but it's difficult to give a theorem. From sphere, the theorem is bigger. But we starting this study. Here we have some main reference. Thank you very much. Happy birthday, Professor Saek.
Comments?
João, what if you consider the domain not orientable?
This is a good question also. We started the investigation about this, but is not, we don't have no result yet, but we are considered, but it's more difficult. There is some results given by Ingrid and Regilene that we are studying to start this study, but we don't have no result in this line.
Other questions or comments? I have some no comments. As far I've been following your work on this subject for a long time, there is a big avenue of possible problems to generalize this. For instance, if you go to S2, not to S1, and if you go for a bigger space than in the source, if you have a more than two-dimensional space. Have you done something on these directions? There are only two different directions.
Yes. And this direction, we can relate it with the classification of Mbhb included.
That was my second question. If you go, for instance, to S2, you have not only Morse functions, but you have the stable functions in place. That you have the singularities, which are fold maps, or folds, or the cusps. Maybe you can do something in this sense, considering this kind of, in the target you have S1, not S1, but S2. And I think that it's quite a very interesting
but I think
way
it's,
to go.
It's not easy.
Not easy, but you are a young boy yet. You have a long time to do it.
Okay.
I guess this is related to the question about the higher dimensional domain. I'm interested in circle-valued maps on three manifolds. So suppose you have a three manifold that has a singular fluoration by surfaces and a circle-valued map on that three manifold. And the singular fluoration is such that on all but finitely many of these surfaces, your function restricts to a more spot function on these surfaces. Is there some sort of combinatorial description that tells you how the graph, for example, changes as you pass through either a function that isn't more spot or through a topological change of the surface?
Yes, good questions. It's interesting, but we don't study at this moment the case where the singular submanifold has dimension bigger than one. Okay, but we have an work about Regilene and José Martínez Alfaro where they study Morse bot function about this line where you are sitting. And we have some example and some motivation, but yet we don't work about this.
Okay, thank you.
Good direction.
More questions or comments? If no, let's thank you, the speaker, again. Hello, everybody. Now we shall begin the second talk of this section. Okay. The speaker is Professor Juan José Nuño Valesteros. I believe that almost everybody knows him very well, but he is a teacher on University of Valencia, Spain. Nowadays, he is a visiting professor of Universidade Federal of Paraíba in João Pessoa, and he is one of the longest data friends of the group, Singularity group in São Carlos. A very, very old friend of me. It's very nice. It's an honor for me to be the chairman of this talk. And he is going to talk on the dual tree of a fold map jam from R3 to R4. Thank you, Juan.
Okay, thank you, Marcelo, for your kind introduction. So really, it's a great pleasure to be here again in person, and so thanks for the invitation. And especially, I had the great fortune of being one of the collaborators of Osamu Saeki, so it's a very special opportunity to be here. So congratulations, Osamu. Okay, so this is a joint work with Juan Antonio Moya Perez from Valencia also. So I forgot to put this reference in the slides. So this is based on a paper that will appear in the Proceedings of the Royal Society of Edinburgh. So it's not published already, but it is online. This is published online. Here you have the reference. Okay, so let's start with the introduction. Then we have here the table of contents. Okay. So the goal is to have a topological classification, a C0A classification of real analytic map germs from Rn to Rp with isolated instability. Okay. So the main tool is the link. So the link, as in the case of varieties in space, is obtained by taking a small enough sphere in the target of the mapping. So you take the sphere in the target, and then you intersect the image with this sphere or the discriminant or so on, and then you construct a new mapping. Okay. So the case where the inverse image of 0 is isolated point is simpler, so I will consider only this case. And this happens always when n is less than or equal to p. So what happens is that the link is a topologically stable mapping between spheres of dimension n-1 to p-1. In fact, it is stable if n and p are nice dimensions, and it is well defined up to C0A equivalence. And moreover, the mapping is topologically equivalent to the cone on this link. So this is the well-known theorem by Fukuda about the cone structure of this mapping. In particular, as a consequence, if the links of two map germs are topologically equivalent, then the map germs, they are topologically equivalent. This is an example. This is the Whitney umbrella from R2 to R3. So in this case, if you take the link, so the link is this, the image of the link is this 8th figure here, and then if you take the cone on this link, you obtain a mapping which is topologically equivalent to the Whitney umbrella. This is not a smooth A equivalent to the Whitney umbrella, but topologically equivalent. So the main questions is, first is to find a good combinatorial model which codifies all the topological information of a topologically stable mapping between spheres. Then another interesting question is about the topological invariance of the link. So we know that if the link are topological invariance, then the mappings, they are topological invariance, but we don't know the converse. So the converse is not clear because if you have homomorphism in the ambient space, these homomorphisms, they do not preserve spheres, Euclidean spheres, so it's not clear, this question. The realization problem is determine which topologically stable mappings can be realized as the link of a finally determined mapping from Rn to Rp. Moreover, to find relations between the analytic invariance of the mapping and the topological invariance of the link, topological triviality of families, and also finite determinacy for topological equivalence. So in the last years, I developed a program with several collaborators to answer partially these questions in low dimensions. So the first one was from R2 to R3 with Rodrigo Martins and Tom Marar. R2 to R2 and R3 with Juan Antonio Moya Perez. R3 to R2 with Joan Acosta and Erika Batista. This is related to the previous talk in this room. R2 to R4 with Rodrigo Mendez, and Rn to Rp for the topological classification with respect to the contact group. This is was a joint work with João Carlos Costa. In other dimensions, the problem is either trivial. For instance, if you take R2 to Rn with n greater than or equal to 5, then you have a knot. You have a one-dimensional curve in a sphere of dimensional D4. So the knot theory in that case is trivial. So this is trivial case, but all other cases are too complicated. So they are too difficult to work with. But sometimes, if you add some additional restrictions, then it is possible to have something. Okay. So that's the case of this talk. And in this talk, I will consider singularities of mappings from R3 to R4, but with the restriction that they are of fold type. So fold type, I will explain. These are the simplest singularities that we can consider in this case. And in that case, we can say something. Okay. In fact, we will have a complete topological classification. Okay, so let's go for some basic definitions. If we have two smooth map germs from Rn to Rp, then we say that they are equivalent if there exists diffeomorphism in the source and the target that such that we can obtain one from the other by this change of coordinates. If these change of coordinates are homeomorphism instead of diffeomorphism, then we say that they are C0A equivalent or topologically equivalent. And we say that a singularity of mapping is stable if any unfolding is atrivial. So this means that if you deform this singularity, all singularities that will appear are analytically equivalent to this singularity. So example of stable singularities, if you take a plane curve, a mapping from R to R2, this is an example, and the only singularities which appear here are the transverse double points, and they appear as isolated points here. So they are the so-called C0 stable singularities. For R2 to R3, so when you have some type of singularities and you go to one dimension more, then you get the old singularities which appear in one dimension more. So this is the transverse double point appear along curves. In this example, you can see this is the curve of transverse double points, and you have new singularities which appear as isolated points, which are with the umbrella. You have one here, and the transverse triple point, which is here. So this is a picture of the stable perturbation of the H2 singularity, which was developed by Marar and Mon in 91. So this is the same singularity, but this is a sculpture that you can find here in the garden, which was designed by Tom Marar. Okay, for R3 to R4, we have the old singularities, which come from R2 to R3, and you have two new singularities, which are the Whitney umbrella and the Whitney umbrella plus a regular point, and also the transverse quadruple points. So could you down the display, please, the screen? Oh, no. Okay, so here is the quadruple points is here, okay? Well, another important notion is the notion of finite determinacy. So we say that germ F is K-determined if for any other germ with the same KZ, with the same Taylor expansion of order k, they are, oh, thank you, they are A equivalent. And we say that F is finally determined if it is K determined for some K. In particular, we can assume that it is real analytic or in fact polynomial because it is A equivalent to its K jet. By the Mother-Gaffney finite determinacy criterion, it follows that any germ which is finally determined has isolated instability. So in fact, in the complex case, this is if and only if, but in the real case, we only have this implication. So the converse of this is not true in the real case. When you have a map germ with isolated instability with n less than or equal to p, a good representative is a representative F from U to V such that the inverse image of 0 is only 0. The mapping is finite, which means that it is closed and finite to 1. And the restriction to outside the origin, this is a stable mapping with no zero stable singularities. So the zero stable singularities, they appear as isolated points. Then by shrinking the representative, if necessary, you can avoid these zero stable singularities. Okay, so let's introduce this notation. This is the closed disk of dimension p and radius epsilon, and this is the sphere in the target. And we take also the inverse image of the disk, which is denoted in this way, and the inverse image of the sphere. Then Fukurascon structure theorem says, well, this is not exactly the same, but you can deduce this theorem by Fukuda's theorem, is that if you have a real analytic map germ from Rn to Rp with n less than or equal to p and with isolated instability, and Np are nice dimensions, and we take a good representative, then there exists epsilon 0, positive number, such that for any other epsilon between 0 and epsilon 0, so the inverse image of the sphere is also a sphere, which is diffeomorphic to the natural sphere of dimension n-1. The restriction is a stable mapping, and its A class is independent of epsilon. And finally, the restriction to the closed disk is topologically equivalent to the cone on this mapping. Okay. So by definition, this is called the link. This is the mapping restricted to the sphere is called the link of F. And in the case that we are from R3 to R4 with isolated instability, then a good representative means that the inverse image of 0, 0, that if it's finite, and that the restriction outside the origin has only transverse double points, transverse triple points, or Whitney umbrellas. The transverse double points, they occur along surfaces, and the transverse triple points or Whitney umbrellas, they occur along curves. So recall that the zero stable singularities, they don't appear here. Moreover, the link in this case is a stable map, gamma, from 2 spheres to 3 spheres, and then it has only transverse double points, which now they appear along curves, and transverse triple points or Whitney umbrella that they now appear as isolated points. So sometimes when you work in topology and you want to obtain global information, then you go to the local, no? But in this case, it's the opposite. You want to find local information, and then by taking a small sphere, you get the local information from the global information, okay? Well, as a consequence, if the two map germs have links which are topologically equivalent, then they are topologically equivalent, and of course, we don't know yet about the converse. Okay, so let's go to the class of singularities that we are working with. So we say that a map germ from R3 to R4 has fold type if it has Tom Boardman type sigma 1, 0. So by definition, this means that, so the first one means that F has corank 1, and the second zero in the symbol means that if you add here M1, M4 are the maximal minors of the Jacobian matrix of F. This is the extended map. So if you consider the extended map, this has corank 0. So here, corank is equal to the maximal rank, which is 3, minus the rank. So F has corank 1 means it has rank 2, and the extended map with the minus of the Jacobian has maximal rank, has rank 3. Okay. So the main result is the following lemma, is that the following statements are equivalent. First, that F has fold type or Tom Morman type sigma 1, 0. And the second is that the multiplicity of F is equal to 2. So by definition, the multiplicity of F is the dimension of the mother's contact algebra. This is the A3 is the local ring of smooth functions from R3 to R. And this quotient here is the ideal generated by the components. So the case of multiplicity 1 corresponds to the regular case, of course. And so this multiplicity 2 means that we are working with the simplest class of singularities that we can consider in this case. And the third statement is that F admits a prenormal form of this type. So is A equivalent to a map germ of this type, X, Y, Z square, and this Z times P of X, Y, Z square for some function P in the maximal ideal. So this was obtained by David Mond in the case of R2 to R3, and using the same arguments, it's not difficult to see that it works also for R3 to R4 or even in higher dimensions. So now it's necessary to introduce this notation. This DF is the so-called double point locus, and by definitions, this is equal to the points A in the source, such that either it is a double point in the usual sense, so this means that inverse image of the image is different from A, or F is not immersive at A. So when you have isolated instability, this is exactly equal to the closure of the points which are strict double points. And the corollary says that if you have a map germ of fold type, as in the previous prenormal form, so this one means this. So you consider this prenormal form, this is one. So if you have a map germ of fold type with this prenormal form, then F has no triple points. The double point locus is given by this equation, this map P of X, Y, Z square equal to 0. In particular, this implies that this double point locus is symmetric with respect to the plane Z equals 0. Also that the image of F is contained in this hyperplane, in this this half space, Z greater than or equal to 0, and also it is symmetric with respect to the hyperplane T equals 0. And finally, that the image of F intersection with the hyperplane T equals 0 is exactly equal to the set of double points in the target. So the image of the double point locus. Okay, so now we introduce the main combinatorial object that we will use for the topological classification. So by definition, a mosaic is a pair D2K, where D2 is the closed to disk, and where K is a closed one-dimensional submanifold with boundary, such that the boundary of K is equal to K intersection with the boundary of D2. And we say that two mosaics are equivalent if there is a homeomorphism between the disks, such that phi of K is equal to K prime. So this is an example. So you have the closest to disk, and K is a one-dimensional submanifold with a finite number of connected components. Some of them are components which are simple arcs with the ends in the boundary of the disk, and some others are closed curves in the interior of the disk. Okay. So given a mosaic, we can associate a graph such that each vertex of the graph corresponds to a connected component of the complement of the K. And you have an edge given by two vertices, Vi, Vj, if and only if the respective connected components are separated from each other by a connected component of the curve. So here we use this notation. So the star is for vertices which correspond to boundary connected components, and the dot for vertices of connected components which are in the interior. And we call this the dual graph of the mosaic. So here you have an example. So for instance, this connected component here gives this vertex, which is of type star. Then adjacent, you have another one, which gives this vertex. You have another vertex here, but inside we have one connected component, which is interior, which gives this dot, and inside this you have another one, which is a dot. Okay, so this is the dual graph. Okay, it's a very simple combinatorial object. Okay, so the theorem is that if you take a graph with vertices of two types, of type star and of type dot, then this graph is the dual graph of a mosaic if and only if you have these two conditions. The first one is that this gamma is a tree, so this is a simply connected graph. And the second one is that gamma has at least a vertex of type star, and if it contains two or more, they are connected by a path that doesn't contain any vertices of type dot. Okay? So, because of condition one, the dual graph of any mosaic is a tree, so we call it the dual tree instead of the dual graph. And to understand better the structure of this dual tree, you can see that the subgraph of gamma given by all vertices of type star is also a tree, which we call the trunk of the tree. So in this case, if you look at the picture, so if you this part, this is the trunk, this stars, the part with the stars is the trunk, and the other connected components with the dots we call the branches of the tree. Okay. So you have each connected component of the subgraph given by vertices of type dot is also a tree and is connected at most to one vertex of type star, and these are called the branches of gamma. Okay. Okay, so the natural definition, of course, is that two dual trees are equivalent if they are isomorphic and the isomorphism preserves the type of the vertices. So the bijection between the vertices sends vertices of type star into star and vertices of type dot into dot. And the main theorem is that two mosaics are equivalent if and only if the dual trees are equivalent in this sense. Okay, this is not difficult. The proof of this theorem is easy, and you proceed by induction on the vertices. So you choose a final vertex of the tree. Because it is a tree, you always have a final vertex, and you can remove this final vertex, and this gives another graph which is also a dual tree. And then by induction, it's not difficult to prove this. Okay. Okay. So let's go now for the dual tree of a stable map. So we consider the sphere in R3 of dimension 2 and the sphere in R4 of dimension 3. So we say that a stable map gamma from S2 to S3 is folded if we have this. Gamma has no triple points. The double point set is symmetric with respect to the plane z equals 0, with respect to this okay. The image is contained in this region, z greater than or equals 0, and is symmetric with respect to t equals 0. This is in the target. And the intersection of the image with t equals 0 is equal to the double points in the target. In particular, this implies that the image of this, which is one-dimensional, is contained in this region T equals 0 and Z greater than or equal 0 intersection with the 3 sphere. But this is exactly the hemisphere, the positive hemisphere, which is diffeomorphic to the closed two disk. Then it follows, in particular, this follows that we can consider this as a mosaic. Okay. Well, one remark is that if you have a map germ which has fold type, then its link can be seen as a folded stable map. Here, this is up to A equivalence because this is not a natural sphere. So you have to take care that you have a diffeomorphism which preserves the symmetry of the mapping. Okay. So by definition, by construction, if you have a folded stable map, then the double point set in the target is a closed one-dimensional submanifold with boundary, and the boundary is actually corresponds to the boundary points of the sphere. And then it follows that this is a mosaic. We call dual tree of gamma to the dual tree of this mosaic. Okay. Okay. So the next examples, some examples, the link of the immersion. So how much time I have? It's over? Five minutes? Okay. So these are some basic examples. You take the link of the immersion and the link of the Whitney umbrella. This is the mosaic and the dual tree. Some other examples, the link of this map germ. This is the mosaic and the dual tree. One more. And this is important that you can perform the following operations. If you have a folded stable map with a dual tree and you take a final vertex, then you can construct a new folded stable map such that the dual tree is obtained after the dual tree by eliminating these vertices. And we have also the inverse operation, and we have two cases. One case is when the final vertex is of type dot. In this case, we use a symmetric version of the universal unfolding of the bigerm of dimension 1, with corresponds to two regular branches with this type of contact. So you can eliminate this. This is a component which is in the interior, and you can eliminate it. And the other case is when you consider a final vertex of type star, and in this case, we use the universal unfolding of the S1 plus singularity in Mond's classification. This is a lemma that if you have any mosaic, then you can construct a stable mapping such that the associated mosaic is equivalent to this. And the theorem is that if you have two folded stable maps, they are topologically equivalent if and only if the dual trees are equivalent. As a consequence, we have also the analogous theorem for map germs. You have two map germs, F and G, from R3 to R4, which are analytic with isolated instability, fold type. They are topologically equivalent if and only if the links are topologically equivalent. And this follows from the combinatorial model. Okay. Okay, and just to finish that, just to say that this mosaic and the dual tree is using this, it is not difficult to give an algorithm to construct any stable type. If you take any dual tree, then it can be realized of the dual tree of a map germ from R3 to R4, which is analytic with isolated instability and fold type. And as an example, you have here some list. So you have to choose conveniently the function P, but some of them are very easy. But for the other, which are more complicated, for instance, this one, so you only have to put, sorry. Oh. You only have to choose in a smart way the coefficients of this polynomial, and then you can get the corresponding components which realize the mosaic and the dual tree. So this is an example of realization of dual trees with up to 4 vertices. This you have one more here. This is a second list. So you can see that, well, it's not difficult. Just you need some experience, and then you can find conveniently this polynomial. And there are more here. Okay, so this is then. Okay, I stop here. Thank you very much. Okay.
We have a few time for questions or comments, please. There are.
You said that there's an algorithm to find these equations.
Yeah.
The other way around, if I give you an equation, do you think it's feasible to write down an algorithm to determine your graph?
Yes, a good question. So we do that just by taking a program like Mathematica or something like that, yeah, that you can represent the image of the stable map. But then by looking at the image of the stable map, of course, you can recognize the dual tree. But we don't have a automatic algorithm to do that. We do that just by looking at the picture.
Okay, thanks.
Would be interesting to have one if you want to join.
Any other comment or question? If no, so let's thank the speaker again. And we shall resume in 5 minutes here for the last plenary talk of this morning. 11:30, okay? Hello, everybody. Now we are going to introduce the last speaker of this morning, Professor Jean-Paul Brazile. He's from Lumini, Marseille, France. He is also, as far as I know, there are two people that I know that have been in all the workshops that were organized at São Carlos and at Marseille. Cidinha and Jean-Paul. I lost one. I don't know if someone has one lost else like me, but they are both people that have been here all the time, not for the workshop only, but for a very, very strong relationship between the Singularity Group of São Carlos, a great friend. And now he is going to talk from SAEC to, from SEC to SAEC. Okay, thank you, Jean-Paul. Please take care.
Thank you. How long I have? 2 hours or 3 hours? Okay. Okay. Yeah. Okay. Okay. It's okay. 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 So I was saying that thanking to all people in São Carlos, many Cidinha, and what is the strength of Cidinha, and it is the fact that this year, and it was organized by young people, and they are taking the relay to continue, and so that's very nice, and I am very happy of that. And so we have already insurance that we will meet in 2 years, and then every 2 years. I don't know how long, but okay. So my talk will not be a mathematical talk at all. It will be more or less like a chat, and I will give a motivation of my talk soon. I have to. Oh. Okay. So this is my the title, and with involuntary participation of TUI and Osamu. So thanks to them. So the motivation is, in fact, the starting point was in São José do Rio Preto in 2016. I gave, in fact, TUI and myself, we gave a course in what is called CEMAT. CEMAT is Semana de Matemática, is a mathematical week, if you wish, for students, mainly for students. And so we gave a course on the Euler formula, and explaining also the Cauchy proof of Euler formula. So that was in, and we proposed a paper, an article in a journal which is called Mathematica Universitaria in Brazil, and which is a nice journal, but I don't know if it continues till now. But the referee rejected our paper. He said this is not it's a mistake, and the reason is he gave Elon Lima sentence. Elon Lima is I think many people, even not Brazilian, know Elon Lima. He made a lot for mathematics, for developing mathematics in Brazil, and I have to say that I respect him a lot. He made a lot. He is very nice. He has very nice books from Elon Lima that I recommend even for foreigner people, not Brazilian people. But as Elon Lima is a man, human, and as we say, a human can make mistakes. And in fact, in this sentence, there are two mistakes. The first mistake is that is to call Euler theorem. It's not Euler theorem, because Euler gave the formula in a letter to a friend, as you know, Goldbach, and so he wrote a first paper to prove, but with a mistake in the proof, and he wrote a second paper and already with a mistake also. So in fact, Euler never gave a good proof of the formula. So that is an important point. And you know that there are many discussions to know if it was already a formula given by Descartes, because Descartes gave a theorem with a proof, which is in fact equivalent to the Euler formula. And Descartes was 100 years before Euler. And so many people say that, in fact, it's a Descartes formula. But the formula was, in fact, proved also by Cauchy. And Cauchy also, some people say that Cauchy proof is not correct. You have the book by Lakatos. I don't know if you know that book. And in fact, Lakatos gave also a counterexample. But all this story about Euler formula you can see in a book. Oh my God, it will come back. There is a book about Euler formula, which is very famous and very nice. That I will give the reference for that. To come back to my story, in fact, Thuy and myself, we completely, that is the second mistake of Elon Lima sentence. He says that it's impossible to give a correct proof, elementary proof of the theorem between us, the formula, in fact, with the Cauchy method. That is, in fact, never say that it's impossible to find a proof of. Never say that. And in fact, with Thuy, we gave an elementary proof of the formula using the Cauchy method, and that appeared in topology and applications last year. So you can give such an elementary proof using only a Cauchy formula, and I recommend, of course, that paper. But the story is not finished, because, in fact, after that, we learned by, in fact, Claudia Adabo. She's an Italian researcher in history of mathematics, history of sciences in general. And she was a specialist of, she is a specialist of Italian monk, Francesco Maurolico. Francesco Maurolico is, as you see, I put for memories the date of all people, Descartes, Euler. Legendre is there because Legendre is the first who gave a correct proof of the Cauchy, of the Euler formula using Descartes. And so Legendre and Cauchy. So, but Francesco Maurolico is in Christmas 1537. So it's a long time before. And he wrote in Latin, so I let you, of course, I think you are all specialists of Latin, and you understand very well. So I put in English also. So in fact, Francesco Maurolico was looking at all planar representations of a polyhedra, platonic polyhedra, which are the 5 regular convex polyhedra. You know, the tetrahedron, the cube, icosahedron, dodecahedron, hexahedron. So you have here some, these are the original picture by Francesco Maurolico. He was writing in Latin, but for pictures, he was writing in Greek. So you have the Greek name of the figure, octahedron for the two first, and then icosahedron and dodecahedron. So Francesco Maurolico was looking at all possible planar representation of these 5 platonic polyhedra, and he observed that if you take the number of vertices plus the number of faces minus the number of edges, you find 2. For this, of course, it is only for these 5 platonic polyhedra. The Euler formula is for all convex polyhedra, not necessarily regular. But Francesco Maurolico, on my viewpoint, is the first who gave this formula, of course, for platonic polyhedra, but the story should be revised because Francesco Maurolico, as you see, is well before Descartes and well before Euler. So that was my motivation, because I came sometimes in Japan, and you will see why I was interested in a little later. And I asked myself, is it some Japanese who discovered this formula? And unfortunately, the answer I can say before continuing, but for the moment I did not see. I did not find. Maybe Osamu or other Japanese know, but I did not. I spent a lot of time. I looked at a lot of papers, and I did not succeed to find. But in fact, this is the map at the time of Maurolico. Oh, sorry. At the time of Maurolico, Maurolico was in Sicily. Okay, so I have to push here. Yes, so it's in Sicily here, and Archimedes before Maurolico, he was here. It was here on the beach, you know, and Maurolico was in Messina, which is a city just here. At that time, the Sicily and Sardinia were property of Spain at that time. And you see how was Germany, how was Italy at that time, not at all unified. And what is for me very interesting in this map is Lithuania. Look, Lithuania is something like that now. And look at it. It was going to the sea. Lithuania was a very big country, and also Poland was not at all the same shape than now. So this map is interesting. Descartes was here in Stockholm at the end of his life, and Euler was somewhere here in Germany. Okay, so at that time, Brazil was very simple. The map of Brazil was much simpler than now. This is after the Tordesillas treaty, Tordesillas Treaty, separation between we're taking just this line. On the right of this line was given to Portugal. On the left of this line was given to Spain. Okay, and Brazil at that time was divided in a very easy way. And at that time, okay, and at that time, Japan was the capital was Edo, not Tokyo. The name changed later, and this is the Edo period. This is during the Edo period, which is from 1603 to 1867. Okay, so this is a period during that time, Japan was completely closed. It was impossible for foreigner to enter in Japan. It was completely separated of the rest of the world, and there was no connection, commercial or scientific connection between Japan and the rest of the world. So I was very interested at that time, because after which is the Meiji period, after that, Japan was open to the rest of the world and received all scientific publications. So it's, if you want to search for Euler formula, it's not during Meiji period and later. It is during Edo period that you have to search and to see if some people gave this formula in Japan. So at that time, mathematics were well Japanese. It is a period of Juan. If I don't pronounce correctly, you can correct me. Juan was, it means Japanese arithmetic, Japanese mathematics. Okay, so it is typical Japanese, and it was a way to speak of mathematics in a very different way from us, from the Western way to speak of mathematics. For example, they did not write proof of theorems. The word theorem did not exist. For them, it was just a way to make a computation in a nice way and a easy way. So the most important at that time was Yoshida Shishibei Koyu, sorry. And he is author the most, the first known Japanese mathematical text. And he was, in fact, using Soroban. Soroban Soroban is this abacus that you can see on the picture. And so at that time, they were, the mathematicians were giving a way to use Soroban for doing everything, including square and cube root operations. I don't know how they were doing that, but this is very interesting. And here are people doing Soroban. The picture is not very good. So this is a Soroban. I have to say that all pictures I show you, I did not ask for permission to use them. So don't. But this is my personal collection of Soroban. So this is a picture that allowed without any problem. And in fact, I have, as I say, this is my full collection. My full collection. I have 3 Soroban, which are Japanese. Okay, Soroban is Japanese, and 1 Swanpan, which is Chinese. And you see the difference between Chinese and the 3 Japanese. There are some difference. The first difference is the ball that you move. Round are like part of sphere for the Chinese, but for Japanese it is a double cone, and it is easier to move, to change. Okay, and Soroban, other difference is that on the upper side of the abacus, you see that on the Chinese there are 2 balls, on the Japanese there are only 1. Okay, and also I don't know. I have find very different explanations on the number of balls in the lower part. Here, Chinese and Japanese, they have 5 on the lower part, but during a time in Japan there was only 4. So I don't know if now it's 5 or 4. Now it's 4. So these are old one. Oh, so I have a very good collection. Thank you. So, and in fact, as I said, at that time, people were learning how to do that, how to do Soroban. And at school, they were even going very fast to make computations. And in fact, they were they were taught to do mentally Soroban, not physically. So they had to think. If I made, for example, 2 + 3, they have to think in their mind, not doing with the physical Soroban. And it's the reason for which they were going very, very fast because they had not to move the balls. They were doing mentally. So it's absolutely fantastic when you see that. So this guy also is. I like this guy. He doing computations, Soroban. Okay, and this is Seki. I said my title, from Seki to Saeki. So here is Seki. It is the guy that you have seen on the first slide, and he is from 1642. Not more or less. We don't know exactly when he was born, but he died in 1708. This we know. And so this is Seki Takakazu that I present to you. And Seki was one of the main mathematicians at that time of Wasan, and he made I put here not to see relation with Seki with others, because as I said, Japan was completely closed. It was impossible to have relationship with other people, but just for you to know people who are more or less at the same time than Seki. Takakazu. Okay, so this. And some achievements of Seki Takakazu. I remind you that it was not necessary to give a proof of theorems, only giving the way to compute, to make computations. But he made improvement in the use of Soroban that we have seen. But Seki Takakazu gave the value of pi with a 10 decimal. The unit of him came to 51 decimals. Okay, and he introduced algebraic notations. For example, we use x for variable, and Takakazu introduced some character, Chinese character for the variable. And he gave also the beginning of elimination theory based on resultant. This was, in fact, made by Bezout, but later on, as you can see, it was later. The notion of determinant was also in Seki. Seki gave also the notion of determinant up to 5 by 5. And at the same time, Leibniz was doing 3 by 3. So it's good also to know that. And the Laplace formula for determinant was given by Takakazu. Also, sum of powers, many things. For example, development of arc sinus. They were knowing very well at that time the development of arc sinus, things like that. Okay, before Western mathematicians, and so that is one of the reasons that I said, oh, it should be a Euler formula somewhere. And as I said, for the moment, I don't know. Okay, but that was my motivation to find if Euler formula was known by these people. And Takakazu, he published. In fact, it was after his days. The students of Takakazu published this Atsubi Sampo. math textbook to clear up mysteries. And I give 3 references here. There is a lot of publications about mathematics during the Edo period, during the Wasan. And it's very interesting to, so if you are interested, these 3 are the 3 basic one, I will say. In fact, the first one was by Annick Oriushi. She married a Japanese guy, and it is her thesis in Paris in 1994, but it is now, I have seen just before, that it is now published by Birkhauser in English. So the first one you can find in English also. But it's these are very interesting because I give all development, and I was always searching by my Euler formula, and I did not find. This is a page from Seki publication that we have seen before, and here he gives binomial coefficients and Bernoulli numbers before Bernoulli. So this is interesting also to know. How much time I have? Huh? Okay. So another thing very important, and that in fact was my main motivation, is during this Edo period, you had what are called sangaku. Is it all correct? So sangaku is very interesting phenomena in Japan, and I don't know any such phenomena in other countries. Is that people were writing mathematical problems, and in fact, I will show you some sangaku in the following, and mathematical problems with pictures, very nice pictures in general with colors and so, and they were giving the problem. The problem were mainly in planar representation, and for example, I will give you examples. But before, it's important to know that this sangaku, here there is one here you cannot see, but I will show you in details in the following here. Oh, okay. So in fact, they were in temples. In the sangaku, people were putting sangaku in the temples, as you have seen in the previous slide. Okay, so they are a small temple and a big temple, but all they were putting these problems in temples. One of the reasons is that many people, quite old people, were going to the temple to pray, and so they were able to. That was the best place to make publicity for. If you have a problem, mathematical problem, it's a best place for making publicity for this problem. To put this problem in the temple, because all people will pass there and will see the problem. And so there are many explanations. Of course, why temples? I just said why, because it's the best place where all people will pass, will go. And so there are also many explanations. Are there votive tablets for some deities? Or, of course, it's a proof of the talent of a mathematician, because the problem you will see are not so obvious. Is it an ex voto, like in some such church? There are many explanations for the sangaku. Here is a sangaku, the one you have seen in the previous slide, and I give you here best slide. As you can see, there are many sangaku problems with circles, with also problem of angles, many problems are asking for relation between, for example, for this one on the right here, many problems. What is relation between the radius of this circle? That is typical problem in the Sangaku. Very often it's such problems. Here is another. There are many Sangaku also with I do not remember how. The second one is fan. Thank you. So many Sangaku is fan, of course. We are in Japan, and the last one on the right is very funny because the guy was already thinking of earphones in year 16 something. So it's very funny. But in fact, it's also a problem about relation between the radii of the circle, and so you can ask Japanese people to to give you the problem which are written here. So anybody was able to write Sangaku and to put in the temple. If you had a good problem, for example, a conjecture, why not? At that time, if you were Japanese with a conjecture, it was possible to write the conjecture and to put in the temple. And this was also a proof of that you are quite a good mathematician. These are other. I like also, it is this one. Yes, this one. No, it is this one. This one, you can see a kind of torus here. The third from the right. Okay, it's like vector field trajectories on a torus, and so I don't know if it is related to Poincaré theorem for I don't know. Maybe looking at what is written in Japanese, we can know. So it's funny that and there is a lot in Japan. I think the one that are known now are 800 Sangaku, but there was more than 1,000. It was a lot of Sangaku, and many have been lost by fire or because it was not well pictured or things like that. But this is a very interesting thing at that time of Wasan, at that time of Edo period, where Japan had no connection with the rest of the world. So this is, I think, very interesting, and so you can see also a lot of publication about Sangakus. And one of a student of Seki Takakazu, the name is Matsunaga Yoshizuke. He gave me hope in my search because he wrote things like that, looking at volume. He was, in fact, in some Sangakus, there are also problems of surface, computing surface, or computing volumes. And so this guy compute a lot of volumes. And this one, I thought that I found, but not. It is a computation of volume, not at all Euler formula. But what is very interesting is that this picture is more or less the same in Euler proof of his formula. So I was hoping that this guy will give me the answer to my search, but not, unfortunately. But is not so far. So, but here is for computations of volume. Of course, you can imagine that there was when the emperor in 1867. They decided to abandon Wasan, and they created Western mathematics, which are Yosan, Yosan. Is it okay? Yosan, Western mathematics, and took place in 1872. It was decided by the government to abandon, to give up Wasan and to use Western mathematics only. And you can see that, of course, it was not so clear for people because there was many people adopt of Wasan, and they wanted to keep Wasan and not taking Western mathematics. So also in the Tokyo Mathematical Society, there was a big discussion between people at that time. Shall we abandon Wasan or not? And in fact, some people say I don't think I agree with this. With the last sentence. So this is, oh my God, I don't remember where I took that, but for people interested, I can find. Oh, sorry. So the last sentence, Wasan will not have had the power to raise Japan to its present level of scientific achievement. So some people say this, Smith and Mikani, Muwata. I don't know what is opinion of people now. If Osamu, I don't know, maybe in private conversation you can tell me if you agree with that or not. I don't think it's clear, this. I don't think, but I don't know. If would Wasan, you have seen that Wasan gave already some improvements before Western mathematics. So this is a big discussion till now, I think, in Japan about Wasan and Yosan. Okay, so it was beginning of 1872, beginning of Meiji period. Period began, started before 1868, but there was an act of a government called Gakusei, and you see Gaku, that you know the sign Gaku here, and only Wasan was to be taught as arithmetic in the schools. So, but that is not abandon of Soroban. I think Soroban continued, no? Continue at school. Yeah, so Sangaku, you have no more Sangaku, but Soroban, the use of Soroban continue. I thought I had taken out that one, but it's I like that one because you see, it's not in English, and it's very funny. I took that picture in Gunma prefecture, in some park, and the park is Uira Mashi Prefeitura, the prefecture. And so I was very astonished to see this in Japanese and in Portuguese. And so it's not at all the park we will go tomorrow, because you see that there are two things. The first is, oh no, oh my God, I am very bad for these things. So the number 2, it's not allowed to make fire, and it's prohibited, it's forbidden to make churrasco. So it's not at all the part we are going tomorrow, I think. And the third, no further uso de bebida alcohólica, so this is clear. No alcoholic drink in the park. And in fact, I learned that many Japanese people who came in Brazil and going back in Japan, they came to this prefecture in Gunma. No. So, in fact, I I had also hoped to find a solution of my motivation because I came in Japan from north to south, from Tatsuo Suwa in Hokkaido to Shoji Yokura thank you, in Kagoshima, and also, of course, Osamu, and people like also Eizuke Hironaka and Shioko Ishii and Mutsuoka. So many people invited me, and so going in Japan, more or less in whole part of Japan, I was hoping to find the solution, but not. What I found is a park where churrasco and caipirinha are prohibited. So, but I found a modern Sangaku. I say that Sangaku disappeared, but not at all, not at all. And I was very happy to discover a modern Sangaku that here. So maybe you know this Sangaku, no? No? Oh, if you go to a page of a famous Japanese writer, is Osamu Saiki. And this Osamu, I was very astonished because I wanted to look at also to Osamu developments. And when you look at Osamu Saiki on the web, you see a picture of Osamu and Japanese writer. Do you know that? You have to go. Japan, it's not written as a mathematician, but you are on the web. You appear as a writer, so it's very nice. And on the web page of Osamu, this is Sangaku on the web page of Osamu. The problem is right here. The problem of this Sangaku is written here. In Japanese, but I wrote also, I put with Google Translation, the real answer is waiting for you. So you see, it was not answer to my question, but and no textbook, is it correct? And at the end of freedom, maybe you will say something more about this during your lecture. I would be happy for that, okay? So this is a Sangaku made by a modern mathematician, writer, Osamu Saiki. And happy birthday to you. And he's nice, no? So I took you from Seki to Saiki. And thank you a lot.
Thank you, Jean-Paul. Are there any comments or questions?
Your talk has made me very curious about the history of mathematics in Japan. The Wazanists, were they sort of gentlemen of leisure? They were not really middle-class people?
Sorry?
Is it true that the Wazanists, that is, the mathematicians of Japan, were not really middle-class people, but they were sort of gentlemen of leisure?
Yeah. They were at the Edo period. Sometimes mathematics were looked at as an art, as something like you see, and we can say that mathematicians at that time were also, I think we can say they were also fan of art. For example, the Japanese stamp have been developed at that time. So you see that they were developing a lot during Wasan period, during Edo period, not only in mathematics as I showed you, but also in art and theater, for example, and so on.
And my next question was that in the beginning of your talk, it seemed that the roots of Japanese mathematics came from doing computations. And so if you're interested in developing algorithms, the algorithm is correct. As long as results are in line with reality, then you are fine. But it's more to
Yeah, geometry, as you have seen in the Sangaku, there is a lot of geometry problems on the plane. Not only in the plane, but also in 3 dimensions sometimes. And what I did not say, I spoke of Japanese mathematics as if it was born in Japan, but many were going from China, of course, at that time, and through Korea. Also, Korean mathematics at that time were also developed. And so it was more influence from China, I will say, and Korea. But Japanese mathematics developed a lot by themselves, as you can see in the work of Seki, which was he was doing many things, and not only geometry but also some analytic problem, and he made a lot of very beautiful things. Both of them, Seki and Saeki, very beautiful things.
Are there any comments or questions? I have just one comment, not a comment, but a thank you for this fantastic talk. And I will include in my CV that I was the chairman of this talk of John Paul. Okay. And so thank you again for the speaker.
Thank you.